As the COVID-19 virus constantly changed to adapt and survive, new variants of the virus has emerged over the past 1 year. The recent emergence of the Delta variant is about 50% more contagious and may cause more severe illnesses than previous variants. The World Health Organization experts have warned that COVID-19 may become just another endemic virus in our communities such as HIV, and may never be fully eradicated. Therefore, countries such as Singapore is planning to transition towards endemic living and ease restrictions progressively. However, this increases the chances of large group interactions, such as in eateries and bus stops, which increases the risk of COVID-19 transmission and formation of COVID-19 clusters. For example, cases linked to the Singapore bus interchange cluster have grown to 504 cases as of September 6, 2021. Since the Center for Disease Control and Prevention has stated that one of the best ways to reduce transmission of the COVID-19 virus is to limit social contact and maintain social distancing, it is therefore useful for the general public to be aware of the crowdedness of places they intend to visit in advance. Hence, an AI-empowered crowd counting platform known as crowded.sg was developed to obtain real-time crowd information at locations of interest. However, the platform suffers from low take-up rates and lack of uploads, implying information is often scarce. Therefore, a dynamic incentive mechanism has been incorporated into the platform to encourage user uploads. To demonstrate the use of the crowded.sg platform, let's have a scenario where the user is rushing for class and want to grab a quick bite. The user can use crowded.sg to easily find out how crowded a place is by looking at the color border of the circle markers. The user can then decide to visit stores with green-colored markers which represent the location is less crowded and avoid crowded areas represented with yellow or red border markers. Alternatively, users can search for the location by its name using the search bar. The location marker pop-up provides more information such as estimated crowd count, the forecasted crowd in bar chart and heat map, and a recent image of the location to see how crowded it is. To gather data for our website, drones are being deployed to capture videos of walkways and bus stops. Users are also encouraged to upload pictures of places they've visited onto crowded.sg, which will use artificial intelligence to analyze how crowded a place is. The number of people detected in the image can be viewed by clicking on the circle marker. To encourage more users to upload, we have included a dynamic incentive mechanism to award logged-in users with points for every successful upload. The points allocated for each location are displayed inside the location markers. The monthly accumulated points are then used to compete with other users in the monthly leaderboard. Now, let me walk you through the system architecture of crowded.sg. When an image is uploaded, the web server forwards it to the vision module of the AI engine to be processed. The output from the vision module, such as the estimated crowd counts, will be stored in MongoDB and will be used for training in the prediction module. The uploaded image will also change the environment states of the incentive module and may cause readjustment to the incentive points offered for subsequent uploads. The web server will then fetch the updated information to be displayed in the client devices, which includes the estimated crowd counts and predicted crowdedness from MongoDB, historical data from Google Maps API, and the incentives point from the incentive module. The incentive module uses Deep Network to output an appropriate point level to attract sufficient user uploads while minimizing incentive costs. The input to the network includes current hour crowd level, next hour crowd level, click rate in the past 1 hour, time since the last upload, and upload rate in the past 1 hour. This input helps the agent gauge the platform sensing demand and image upload supply for each location. To visualize the output from the incentive module, we plot a scatter plot to show the points offered for each state. We can observe that the agent is able to make rational decisions by allocating higher points for locations with higher demand, longer time since the last upload and lower upload rate and vice versa. Based on the simulation result comparing the different mechanisms against the next hour demand, we can observe that the dynamic incentive mechanism using DQN is able to adjust the points offered to follow the trend of the next hour demand. This dynamic behavior helps to save significant cost as shown on the bar graph comparing dynamic incentive mechanism against static incentive mechanism at 8 points. Although the total number of uploads using DQN is lower than the static method at 8 points, we can observe from this graph that DQN have lower redundant uploads than the static method at 8 points. In conclusion, the dynamic incentive mechanism implemented is able to save cost by dynamically adjusting points offering based on sensing demand of the locations and helps to encourage user uploads onto crowded.sg. In the future, we plan to explore automated decision-making by providing recommendations on the best route to take to avoid crowds.